Hi, welcome back. In this lecture, I will discuss the matrix transpose operation and its performance modeling. A matrix transpose is an operator which flips a matrix over its diagonal. Simply put, it simply switches the row and the column indices. The matrix transpose is very important kernel when it comes to HPC. For instance, it is widely used in calculating two-dimensional and three-dimensional fast Fourier transform. But let's look at a simple example of how to calculate of a matrix transpose. So in this example, we have a matrix called A. We take the transpose and we store the results of the transpose in a matrix B. So the algorithm itself includes a nested loop going from two indices going from 0 to n, where n is the size of the matrix. So which kind of locality this code has? Well, it does not have any temporal locality since neither B or the A matrices are used after this simple calculation. So the data is only used once. So there is a potential for spatial locality. So spatial locality is only achieved if the one column of the matrix A fits into the cache. Otherwise, each of a column of A might be read several times and to be moved to the cache. Because this operation does not exhibit any temporal locality and potentially has only spatial locality, the transpose is a semi-local at best. So as usual, one of our goals of our course is to provide a performance model to predict the performance of this simple operation. So what is the performance model for the transpose operation? Well, so we have nested loops going from 0 to n, and there are basically two loops. So this operation here in the middle has been is calculated n squared times. So each iteration includes one load of the matrix A and one store on the matrix B. So when it comes to the performance model, we will have n square loads and n square stores. So this is very simple model, exactly like like in the stream. So this simple model predicts exactly the same performance of the stream and benchmark. It's not surprising at all, since the kernels that we are actually running here is just a copy after all. So I run some of these tests and calculate the bandwidth for different matrix size. So on the table here present the different matrix size that have been tested on my laptop, and then here on this column here we have the results of the bandwidth in megabyte per second. So you can see that for a rather small size of the matrix, we achieve a performance of 13 gigabytes per second. That is roughly the same performance that I get, the same bandwidth I get by running the stream copy kernel with 20 million elements. So as you can see, just slightly increasing the size of the matrix, the bandwidth is actually dropping, so it's we're getting rather lower performance, just increasing the size, right? So the performance increase in the size, it deteriorates up to a test case of 8000 by 8000, where I only achieve 447 megabytes per second as a bandwidth. So why the bandwidth is going so low, right? So why the performance is so low? Well, the compiler clearly fails to manage the spatial locality. So we saw that there is a potential for a spatial locality, but the compiler cannot manage to use it. And why the performance collapse at 8000 by 8000 metrics? Well, this might seem large, but it requires 1 gigabyte of memory, so quite a large amount of memory, and it should still fit in the memory. So the question we are going to tackle in this lecture is what might be done to improve the performance. So I have a question, right? So is the question is about how we're going to model the, the matrix transpose operation. So we are going to model the performance of the transport with this simple model. First, we're going to assume that the size of the cache is just a few cache lines. Then we're also going to assume that access to consecutive elements in memory will read from the cache line. That is what we call the spatial locality. Also, we are going to assume that access to non-consecutive elements in memory, the B array, the B matrix in our example, will not be in the available cache lines, forcing a full cache line to be accessed for every store. We also assume that the cache line stores 64 bytes. This is also basically 8 doubles. So what is the time the time cost of a transport with this model? Well, we can use the stream performance data as a sustained memory performance in moving data to or from the memory to the cache and use it in our model. So a simple performance model is the following. So we will have two cases. If the source and the destination matrices, the A and B matrices, will fit into the cache, then the total execution time will be equal to n squared. That is basically the total number of read and store. And in this case, we will use the execution, the time that is required from read and write from the caches. A different case if the source and the destination matrices do not fit in the cache. So in the case that the matrices are too big, they won't fit into the cache. So this will be the our model for predicting the execution time. So it will be still again n squared number of times of read and write, and then we will have the time that is required from loading from the main memory, and also the time that we takes to write in to the main memory, multiplied by L. So what is L in this case? Well, L is the number of elements per cache line. Again, I want to stress out the point. These are not sharp prediction, but very simple bounds that you want to have an idea of the performance when the transpose using matrices exploiting either cache or not exploiting the cache in the system. So let's look at one case. Let's see in practice how this is working out. So I use my laptop as a benchmark, as a test, as a benchmark environment. That is a MacBook, has an Intel processor. I run the stream and get the performance bandwidth. I use a 20 million element array, and I take the results of the bandwidth for the copy kernel. So in this case is almost 14 gigabytes per second. Then I have my test code that is performing a transpose, and I also calculate the bandwidth for this transpose operator. So I just simply compile on my Mac this transport.c source code that is also available in Canvas. So let's look at the performance bound model that we derived in the previous slides. Well, the first assumption we can assume that read and write takes the same amount of time, right? So this is not exactly true for most of the system. Typically, read is faster than write, but just for the sake of simplicity, let's assume that the read is equal to the write. We can then use the results we have from the stream benchmark and the copy, and calculate the time for a read or a write as just an inverse of the bandwidth. So this is the time to read or write 1 megabyte to the memory. Let's go back to the model we derived in the previous slides. So the total time is n squared, where n is the size of the matrix, and then we have the cost for a read, and then we have the cost of the write multiplied by L. In this case, L is equal to 8 because there are 8 doubles in the cache lines. So this is equal to n squared multiplied by n by r. If we want to calculate the bandwidth, so this is simply n squared divided by t, that is equal 1 over n r. So r is 1 over this, so the bandwidth goes at the numerator, and we divide by 9, and we get an estimate of the transport operation performance of 1 gigabyte point 1.5 gigabyte per second. So how this compared to the measurement? So here is a plot. On the x-axis I have n, that is the size of the matrix, and then on the y-axis I have the bandwidth, right? And when I measure for a different metric size and plot it here, I take for 100 n equal to 100, n equal to 200, 300, 400, 500, 1000, 1500, so on and so forth, right? And then I plot here as a function of the bandwidth. So in blue we have the bandwidth that I measured using the simple code in C, and then here in red we have the prediction of the performance when the transport cannot use the cache. So the effects of the cache is rather obvious. As you can see here, when the two matrices can fit into the cache, the performance is very high. So we have a huge bandwidth. The performance drops after n equal to 1000. So, and the reason for that in order to have any spatial locality, we need to have the caches to store at least one row of the target matrix to get spatial locality, right? So in the case of 1000, this basically translates to 64 kilobyte. Well, since n is equal to 1000, L is 64 byte. So as you can see, just using the data that we got from the stream, the estimate is actually quite good, but is not tight, as you can see here in this plot. So why the estimate is not tight? Well, there are some complications coming from how we modeling the hardware and how actually the hardware is implemented. So one question is, how many loads and store from memory are required to make a simple operation like A equal to B? Well, the natural answer that we had until now is that we have one load for B and one store for A. However, for a cache-based system, the answer might be two loads if we have two cache lines, one with A and one with the B. So we could have two loads if we need to load from B from one cache line and A from another cache line. And also we will have one store that is a cache line containing A. So this is typically called write allocate. So instead of having one load and one store, we might have two loads and one store. An additional complication, again, coming from our execution model, so the way that actually we model our hardware, is that when do the writes from the cache back to the memory occur, right? So there are two ways of implementing in hardware. So an answer to this question is, well, as soon as the store happens, right? So we write back to the memory. So that means that this operation is done immediately. This is called write through. It simplifies the hardware design especially when it comes to multi-core hardware design. But increase the amount of data that written to the memory, so is increasing the data movement. A second option is what is called write back, and the, um, the writes from cache back to memory occurs only when the cache line is actually needed. Right? So these reduce the amount of data that is written to the memory, also complicate the hardware in multi-core design. So more advanced systems like server system tend to have this last option, so write back, while the lower performance system, simpler system, have a write through. Yeah. So depending on which hardware implementation, we also have different time um, for modeling the write back to the memory in our model. So I want to address now the second question I have is, can we do something to increase the spatial locality when it comes to larger matrices? And of course, the question is yes. And the basic technique that we're going to use is to reorder the operation so that the spatial locality is preserved. We are going to use a technique that is often called also tiling. So we get our our metrics, and instead of actually transposing the whole column, we select a small tiling, we transpose tile by tile. Right? So this tiling technique has consists of two basic steps. The first step is called strip mining. The second one is going to be loop reordering. So what is strip mining? So strip mining starts from a loop going from 0 to n, and it breaks the loop into two nested loops. So here we have a loop from 0 to n, and then here we introduce a strip that is basically a step. And then we separated the loops in two loops. The first loops is jumping by strip elements, while the other one, the inner loop is basically jumping element by element, right? So this is basically exactly what it is before, but instead of using one loop, we use two loops. So in our case, we have two nested loops in Transpose code. So we'll apply the strip mining to this loop and then to the second loop, and this will give basically four nested loops. So far, keep in mind that we didn't access the data access pattern. So the performance when it comes to caches is still expected the same as like in this case here, right? So basically, what we do, we just go consecutively this inner loop, right, one by one, right, until we reach the strip size, and then there is another counter, the outer counter it goes to a different strip and then consecutively. So the data access pattern is not really changing. We need one extra step. And this extra step is the loop reordering. So what we're going to do is to move the loop over I inside the JJ loop. So we take this loop here and we just simply reordering. Right? So this will allow us actually to have our tiling when we do the loop. So how do we choose this strip? Well, we choose the strip value to fit the two matrices, the two tiles, the tiles in the cache. So we can do this strip mining and loop reordering, for different caches. And then, so one important thing to remember that is even rather small metrics like 1000 by 1000 is 8 megabyte, right? So these metrics they do not fit in in the cache. So we will need this kind of technique, strip mining and loop reordering, also called cache blocking or tiling, um, in order to have a spatial locality. So typically, a processor like laptop or small workstation, they have a L2 that is roughly 2 MB or smaller. In my case, I have a 256 kilobyte per core. So in order to have spatial locality, we do need blocking both for L1 and L2, even for rather small metrics that we think that might fit. They typically don't fit, so we need to apply this technique. So there is an overhead from applying these techniques to the loops. So blocking, strip mining, loop reordering are not for free. There is a overhead with each extra loops and with each block or tile. So that means that in order to have the least overhead, we should have blocks that should be as large as possible, but still ensure a spatial locality. In addition, moving data between each level of the cache is not free, so blocking for each level of the cache might be valuable, and block sizes must be selected for each level. So these are an example where I implemented a version of the transpose code using strip minings and reordering the loop, and then I compared to the performance of the naive implementation of the transport operation. So I choose a matrix that is 4000 by 4000 with a strict value, for instance, here of 16 for L1. So for the unblocked case, that is naive implementation of transform, I get 450 megabytes per second in the case of 4000 size. When I block, I try to block for L1 using a strip size of 16. I get 25 gigabytes per second. That is roughly 5 times the performance of the unblocked version. If I get a strip of 128 elements, I get a smaller performance. So if I try again, if I try to block for L1 using 32 elements, I got this performance that is slightly, more or less the same bandwidth of strip equal to 16. If I use 256 elements for the strip variable, I get 2 gigabytes per second as a performance. So which observation we can get from analyzing this data? The first comment I want to make is that blocking for the fast cache, that is L1, provides significant benefit. So there are smart compilers that can make these transformations, particularly Intel compilers. In some cases, they can do it. Obviously, my compiler couldn't do. I used the -02 optimization flag, and I didn't see any transformation on the naive code that was doing strip mining and loop reordering. So one of the difficulties is that the compiler, they do that only if they have enough information about the data, so the transformation are safe to ensure correctness. So in our models, parameters are many, and models are often not accurate enough to select the parameters. So for instance, how do we select the strip value? So models can help, but sometimes they're not accurate enough to help us in choosing this value. So one question is, why won't the compiler do this? So first of all, as I mentioned, the H strip mining reordering, it does adds an overhead, so more operation actually required. So best parameters values like strips are not very easy to select. So in this case, we will need the compiler to select one of the values for strip, right? And also So keep in mind that with the strip mining, we go from one loop to two loops. We could have potentially two different values for the one for strip in the case of the first loop or in this case of the second loop. Uh, so there are many variables to consider. So the best code and depends on the problem size. For small problems, is typically simply the simplest code is the best. In this case, the naive implementation. So note that some compilers support annotation to the code to perform particularly transformations such as loop unrolling to provide input on the loop size. So there is a possibility to provide the compiler some extra information in the code by adding some annotation to the code. So why actually we don't do this all the time? Well, it's pretty much the same reason why the compilers they don't do it. So it's not easy. It's very buggy prone, error prone, and is sometimes not always beneficial. If the, as I told you, if the problem fits to the cache right away, then there is no use actually in doing this. So by doing that, you also use generality. So the blocking might work only in a very large system, in very large matrices, but it cannot work on small matrices. So compared to the compiler, we do have an advantage is that we have performance models and we have a performance expectation. So we can actually try to predict with our performance model and then measure, right? We also know what is the range, the loop range. So we know if n is big or small. So n is big, so the data won't fit into the cache, and is small, the data will fit in the cache. So we can, so if the n is big, then we can go to tiling, for instance. So one of the problem is that how do you choose a strip and other parameters when it comes to the tile blocking, cache blocking. So we probably, the best way is actually to try all different strip values. So we can actually rely on an automatic way to do that. This is called auto tuning. So we can let a framework, these are called auto tuners, to explore all the parameter space of different parameters and check which configuration gave the best performance. So this is the last slides of this lecture. In the next lecture, I will go back again to the caching and try to make some more consideration about performance when using caches. Talk to you soon.